Okay, so hopefully you have an idea about oxidation reduction or redox reactions. This video is going to tell you a little bit about what we call redox agents. Agents are what cause the change, essentially, during oxidation and reduction. So agents of change, if you will. So the agents are causing the oxidation or reduction in another part of the equation. I want to show you just a quick analogy, and if this works for you, great. If this helps you understand how agents work, great. If not, then just forget about it. But I think it's a helpful way to think about things with regards to what's being oxidized and reduced, and then their role as agents. If you think about this picture, you've got two hands obviously holding hands here in this kind of drawing. And what's going on in this particular example that I want to explain to you is that one of these hands is really cold and one of them is rather warm. Perhaps you've held someone's hand before and they always have cold hands or they always have warm hands. Well, think about it this way. If your hand is sensing cold or warm, the other person is almost certainly sensing the opposite. So the idea is that the hand that's being warmed, let's say the blue hand here to show that it's a cold hand, the hand that's being warmed up is cooling the other hand. So if yours is the blue hand here, you're going to feel warmth coming to you. But if yours is the pink hand here, the warmer one, you're being cooled by the other hand. So while you're being warmed, you're cooling the other, or on the flip side, while you're being cooled, you're warming the other. And if you hold hands with just about anybody, you'll notice a temperature difference. The arrows here sort of toward the center of the hands show that the heat is transferring from the warm hand to the cold hand. So the hand being warmed is at the same time cooling the other. If you're being warmed, you're cooling, and if you're being cooled, you're warming. When it comes to oxidation and reduction, it's very similar. If you're being reduced, you're oxidizing, and if you're being oxidized, you're reducing someone else. So in our agent speak here, if you will, if we're talking about the hands, we would say that while being warmed, you are the cooling agent. And if you're being cooled, you are the warming agent. You sort of are having an effect done unto you, and at the same time, you are causing a change in another. And that's how redox agents work. If you're being part of an oxidation reduction, not only are you doing something, you're having something done unto you, and it's the opposite of what you're causing in the other. So let's look at redox agents as it pertains to an equation. In redox reactions, the atom or atoms being oxidized would be considered to be part of the reducing agent. And on the flip side, the atoms being reduced are part of the oxidizing agent. You can't be chilled and at the same time be chilling someone else. Okay? And you can't be, while you're being warmed up, you're not warming up someone else. You can't kind of do both jobs at once. If I'm being warmed, that means I'm taking in heat. I can't also be giving it back. And if I'm cooling, being chilled, that means I'm giving off heat. And if I'm giving off heat, I can't also be taking it back. And so in the case of oxidation reduction, if you're being oxidized, that's the loss of electrons. And so if you're losing electrons, that means you're giving them to someone else and they're receiving them, being reduced. On the flip side, if you're being reduced, it means you're gaining electrons. You're taking them from someone else. So they're being oxidized on the other side. Let's look at a couple of examples and see if this can make sense. A little bit better with examples to look at. Keep in mind as you're assigning agents, the jobs of oxidizing and reducing agents in an equation, that both the oxidizing and reducing agents must be reactants. In other words, they must be on the left side of the reaction equation, never products. Agents are on the left side only. So, in a redox reaction like this is one that you did on the previous page, or on the other side of the page perhaps. This is number 5, and in the previous video we did this one together. In this equation, hydrogen was being reduced from 1 plus to 0. And since hydrogen is being reduced, it must also be part of the oxidizing agent. Well, in this case, hydrogen is part of water, H2O. And so in this equation, hydrogen is being reduced, and water, which contains that hydrogen, is the oxidizing agent. Sometimes the agents are kind of bigger than that single element that's being oxidized or reduced. In this case, hydrogen is a single element being oxidized within the water, but the water as a whole is the oxidizing agent because it contains the hydrogen atoms. It includes those hydrogen atoms. On the flip side, sodium in that same equation was the element being oxidized from a 0 up to a +1. And since sodium is being oxidized, it's also the reducing agent or part of the reducing agent. In this case, we're looking at sodium that's part of, well, nothing bigger. Sodium is the whole thing. On the left side of the equation, sodium is being oxidized, and sodium is part of itself and nothing more. So in this case, sodium serves both as what's being oxidized and as the whole reducing agent. Sometimes the element being oxidized or reduced is part of something bigger, like the hydrogen is part of water here. The sodium in this case, though, is part of nothing bigger. It's just an element in this reaction. Let's look at a couple new ones together. These should be the ones that are on the second side or the second part of this assignment for redox agents. Okay. And what I'd like to do is just kind of go through a few examples and show you how to think about these. Now, we aren't going to go through and label in the boxes over here the from and to, the before and the after, in terms of the oxidation numbers of the elements, but we do want to figure out who's being oxidized and who's being reduced. So in this first one, we have carbon joining with chlorine to make carbon tetrachloride. And if we go through and assign our usual oxidation numbers, oxygen and chlorine both start out at 0. And in a compound, chlorine tends to take on a -1 oxidation number, and carbon is typically a +4. And those oxidation numbers work in these formulas to make it balanced out. So who's being oxidized? Well, hopefully we can see carbon being oxidized from 0 to 4+. So I would say carbon is oxidized, and chlorine's being reduced from 0 to -1. So chlorine is being reduced. Now, in order to figure out the agents, we want to look at the element being oxidized here and connect that to the reducing agent. So in this particular case, my first column will include the element being oxidized, and my last column will have the corresponding reducing agent that that element is part of. In this equation, carbon is being oxidized, and carbon then must be part of the reducing agent. It's whatever contains the carbon over here on this side of the equation. This is going to be the agent. In this case, specifically, this is going to be the reducing agent. Well, carbon is part of carbon and nothing more. So we would actually just write carbon again as the reducing agent. Chlorine is being reduced in this case. So let's use a different color. Switch it over to red here. Chlorine is being reduced from 0 to -1, and so whatever chlorine is part of as the element being reduced, it'll be part of the oxidizing agent. So these two columns go together in this example. So the element being reduced, chlorine, is part of, in this case, the oxidizing agent. Now, what is it in this case that chlorine is part of? Well, it's part of nothing bigger than itself, but it is a diatomic element at least. So when we put down the oxidizing agent, we can list chlorine as part of diatomic chlorine, the oxidizing agent. So the oxidized element and the reducing agent are connected to each other, you could say, and the element reduced and the oxidizing agent are connected to each other as well. So finding the element being oxidized means you've also found the reducing agent, and finding the element being reduced means you've also found the oxidizing agent. Let's do another example together. This is number 4. In this case, what's being reduced and oxidized? Well, carbon starts out at 0, and hydrogen ends up at 0. In the water molecule, we typically expect to find hydrogen at a +1 and oxygen at a -2. And in carbon monoxide, oxygen's still a -2, and that means carbon would have to be a +2. So, who's changing? Well, carbon's going from 0 to 2+. That means carbon is being oxidized upward. And the element hydrogen is being reduced from 1+ down to 0. So hydrogen's being reduced. Now, what are these elements part of? Carbon, in this case, being oxidized, is part of the reducing agent. So we need to connect this column to this column. The element oxidized, carbon, here at the beginning, is part of nothing bigger necessarily, but it is the reducing agent, or we could abbreviate it as Ra. So carbon is part of the reducing agent, which is itself carbon. Hydrogen, being reduced, is part of the oxidizing agent. And in this case then, hydrogen is part of, as the oxidizing agent, it's part of water. Water is acting as the oxidizing agent here. So the agent is that which contains the element. In this case, the agent contains the element being reduced. Hydrogen is found within the oxidizing agent because it's being reduced. Finally, one other equation on this page, and I don't think this is number 4. I think that numbering is wrong, but hopefully you can find this equation. Let me just see if I've got a copy here real quickly. Well, these aren't numbered. So if you go down the page a little bit, it looks as though this is right around number 10. Okay? A single replacement reaction between zinc and sulfuric acid. So who's being oxidized and who's being reduced here? Well, in our compound, hydrogen is going from 1 plus down to 0. And zinc is going from 0 up to 2 plus. Now, we could go in here and look at sulfur's charge, we could go in here and look at oxygen's charge, and you'd find that neither of those two elements is changing in its oxidation number. In fact, sulfur is at a +6, oxygen is at a -2, and the same thing over here. So just to kind of avoid some clutter, I'm going to leave those oxidation numbers off over here because they aren't changing anyway. So who's being oxidized? Well, zinc is going from 0 to +2, so zinc is going upward. And hydrogen is being reduced from +1 down to 0. So hydrogen is being reduced, like so. Now, what does that mean for us here? The element being oxidized, remember, the element being oxidized is part of the reducing agent. And so the element being oxidized, zinc, is part of the reducing agent. Ra here, reducing agent. Well, it's part of itself. It's nothing bigger. Zinc is also the reducing agent. And on the flip side, hydrogen, here, the element being reduced from 1 down to 0 is part of the oxidizing agent. Hydrogen is part of sulfuric acid. And so we could say that sulfuric acid is acting as the oxidizing agent. Okay? And fit that kind of in my box here. Now, you might find that down the road, if you take AP chemistry or you study this in a little bit greater depth, you might find that we actually sometimes want to sort of take this compound that the oxidizing agent is labeled as here and sort of take it apart, because the sulfates aren't really changing, they aren't really part of the action. And so in a sense, you might also be able to label simply the hydrogen ions within the sulfuric acid as the oxidizing agent. So depending on the source or depending on the outcome we're looking for, you might find that some books or some sources, even me next year in AP chemistry, might show you ways in which hydrogen itself is the oxidizing agent only as the ion, the hydrogen ions themselves. So it's depending on your perspective a little bit. But for right now, I'm mostly concerned with you recognizing that the hydrogen being reduced is part of the oxidizing agent. And that's, in this case, we'll go ahead and say sulfuric acid is sort of taking on that role. Whether we zoom in a bit more later or not, we'll say that for a different day. One more example, and then we'll be done. This is the 13th one, I think, down the page on that sheet. And I wish those were numbered. I apologize for that. But in any case, this is a good example. Something different about this one I want to point out, and that's that iron starts out with a +2 charge of its own and ends with a +3 charge of its own. You're going to find that some of the equations on this page are given pre-charges or sort of pre-assign their charges. Well, these are ions in an equation. This is iron 2 becoming iron 3. Well, hopefully you can recognize that iron 2 becoming iron 3, even without you labeling it at all, is the charge increasing. That's oxidation. So the element being oxidized here is the iron. You might even say the iron 2 plus. The element being reduced is the manganese. Here we've got manganese in this permanganate ion. If each oxygen has a -2 charge, which is the usual charge for oxygen, that means in order to have a -1 overall charge, the manganese oxidation number would have to be +7. Okay? This goes back to things we did last unit, so hopefully this still makes sense. But 4 times -2 gives me a -8, and then my manganese gives me a +7. When I put those together, they overall have that -1 oxidation number or charge as an ion. And on this side, my manganese is a 2 plus. So manganese is going from 7 plus all the way down to 2 plus. That's some significant reduction in the manganese's oxidation number. Now, since the element being reduced is manganese, it's part of the oxidizing agent. And so in this case, manganese is part of the permanganate ion. And I would go ahead and list it as such here. Okay? The whole ion is the agent. Likewise, since iron is being oxidized, as we see here, it's part of the reducing agent. And so this iron at the beginning, remember they have to be on the left side, would be acting as the reducing agent. And in this case, that's iron as the ion 2 plus. Notice how over here, as I'm identifying agents, I want to show for sure all the charges that are pre-written. So I want to show the permanganate with its -1 charge. I want to show the iron with its +2 charge. When we're identifying the elements being oxidized, it's not necessarily the case that we have to show those charges, because the atom of iron, the element iron, is being changed. The element manganese is being changed. Their pre-charge, their ending charge, isn't as important as knowing that's the element being changed. So agents are a little trickier, for sure. Hopefully you finish the other side with some success and confidence. And if you get to this side and you feel like that's been shattered, and now my agents have completely messed me up, give them your best. Always working in pencil is a good idea. And if you feel really, really hesitant, then maybe don't do all of them. Do the first half, or try a couple of those tougher ones toward the bottom, and leave some of the others until you get some reassurance or some confirmation that you're doing it right. Feel free to check with others. Just make sure that you're doing your own work as well. And if you feel real stuck, I'll catch you up the next time I see you in class. Till then, good luck, do your best, and finish up as much of that page as you can figure out.